Yes, because it has so much algebra in it. Okay, that's not that many pictures. But it is a few. All right. So what we did yesterday is we talked about how to find the area under a curve above the x-axis between A and B. And the idea is that we have the curve is well defined. It's a function. We've got a formula for it, but we want to find this area. And you kind of got to take my word for it a little bit that this activity, finding the area under a curve above the x-axis, is really helpful. Okay, for more than just finding the area. Okay, but I think you could imagine there's plenty of good reasons why you want to find the area of something that was maybe curvy, right? There's not, lots of things in the world that are, you don't need to write this down, but, if you have, that are not exactly straight lines and stuff like that. For instance, if you've got a pond or a body of water or a lake or something like that, and it's, the way that you would find, just if you're talking about the area there, you could do the same process. You could approximate it with a square, or if you're able to find, a function that you can, for which that it kind of models that, then you can start to utilize that process. You might be like, well, that's not very helpful because we saw that one of these sides was actually straight. Okay. After we learn some new techniques, though, what we'll find is that if we have a top curve that looks like that and a bottom curve that looks like this, what we'll find, that we'll do this next week, we can actually find the area between two curves using the simple geometric process of find the bigger, subtract the smaller. To find the area of everything under the wavy curve here, all the way down to here, and then subtract out all the area, underneath this open parabola. So subtract all this out, and what's left over is that region right there. And so it doesn't have to look like a sine curve. Doesn't have to look like a parabola. It could be anything else. It could be parabolas and parabolas. It could be something that's sinusoidal, something sinusoidal, or something that's weird. If you can get a function to describe that shape, then with calculus we can find the area between those curves. Okay, and then there's all sorts of other situations you can get that. Later on down the road, this is a Calc 2 thing, not a Calc 1 thing, but with the process that we're doing here, you're also able to find the length of that curve. Okay, using a similar process. You're also, if you can imagine taking this and my engineering students revolving it, okay, around an axis of rotation, okay. Well, you're able. What you end up getting are discs or rings or donut type shapes, and you can find volume. And that's how you define volume of things that aren't completely cylindrical or rectangular in their base. You have that function, then you end up slice it, and then you can figure out those areas. And that's once again with calculus. So that's applications down the road of all the stuff that we're doing. Okay, so just not to mention, you can turn it into something called an accumulation function, which if you have a rate, you can then find out how much is accumulating, which is super helpful in lots of engineering situations. All that to say, the applications down the road for finding the area under the curve are more than just finding that area. Okay, so keep that in mind. That'll be helpful because here, as we get into the middle of things, it's going to be kind of tedious, and you ask yourself, why in the world are we writing all this stuff just to find the area under? There are thousands of applications. Okay, so just let that be your motivation. All right. Yesterday we approximated the area under the curve using rectangles. We also used a trapezoid method. we're gonna focus in on the rectangle method since that's a little bit easier. Some of we had different ways of choosing where to draw those rectangles. What's really interesting is it doesn't actually matter which method you use. Left endpoint, right endpoint, circumscribed, inscribed, rectangles. If in the end you're turning the number of rectangles from like 10 rectangles to 20 rectangles to 100 rectangles to 1,000,000 rectangles, you know, and if you're increasing the number of rectangles used for your approximation, then the area that you're going to be getting is going to be closer and closer and closer to the exact value, okay? So it doesn't matter if you choose your rectangles where the endpoint is on the left or the endpoint's on the right, or however it is. If you, as those rectangles get thinner and thinner and thinner and thinner and becomes more and more and more and more of them, then, like I said, that approximation becomes closer and closer to the exact. So what we're going to do is we're going to choose a method that is actually just whichever one is the easiest algebraically to deal with, and that's the right triangle method, or sorry, the right endpoint method, okay? So we also said that each one of those rectangle widths was delta x, which is b minus a over n. We'll visit that as well. So here we go. So a new take on that old picture. I'll divide this into 4 regions. And we will use right endpoint rectangles to approximate it. Or actually to kind of set up our statement. So what we're going to try to do right now is come up with a complete generic formula that would work for any function, for any number of rectangles, so on and so forth. So each one of these widths is delta x. So we can think of this point right here as a plus delta x. And we can think of the height of this particular rectangle as f of a plus delta x. See if that makes sense to you. I think yesterday as we were doing this and we were plugging in numbers, I said, how are we going to figure out how high this is? I think it was Hector who said, plug it in. I said, which number are you going to plug it in? He said, well, this x value right here. So in this case, since we're kind of doing things algebraically, this x value is just a plus delta x. Class, what would this x value right here be? This x value right there.
A plus delta x plus delta x.
Okay, yep, a plus delta x plus a delta x, or a plus 2 delta x. So then what would that y value right there be?
F of a plus 2 delta x.
Yeah, f of a plus 2 delta x. And this x value right here?
A plus 3 delta x.
Yeah, f of a plus, whoops, not f of, it's just, that's just a plus 3 delta x. And then its y value would be f of a plus 3 delta x. And you know, now I put 4 rectangles there, but we could easily imagine, you know, this could just be the first 4 of like 50 or 100 or an infinite number, okay? So our area approximation would be the area of this rectangle. So I'll say f of, so it's going to be the the height times the width there. So f of a plus delta x times delta x. That's the area of the first rectangle. Plus area of this next rectangle. So f of a plus 2 delta x times delta x. So the height times the width. Evan, does that make sense?
Yes.
The area of this rectangle is just going to be its height times that width.
Yes.
Plus, put it over here, f of a plus 3 delta x times delta x plus dot dot dot. And we would continue going on for as many rectangles as we had. In this case, I've got 4, but I'm going to kind of leave it open-ended to be, you know, there could be 40 or 400 or 4 trillion. In fact, we want to go way past 4 trillion. We want to go to where there's an infinite number of rectangles. We want to see what that pattern will be. So we can definitely see what's going on here. We have each one of these terms. There's only one thing that's changing. What is that thing that's changing?
The number in front of delta x.
Yeah, number in front of delta x. So what I'd like to do is I'd like to condense that into a single statement. And I cannot remember how much we covered this in pre-cal last year. But when you're adding a whole bunch of things up, there is the symbolic notation for that, and that is the summation. And we would say f of a plus, and we'll use a counter variable, I. We'd say f of a plus I delta x times delta x, where it's basically this term repeating over and over and over again, and the sigma here tells us that that's adding those all up. And we need to know what values are acceptable for I. We would say for I equals 1 up to n. Those of you in programming familiar with the for loop, right? And that's our area approximation. Where delta x equals b minus a divided by n. Okay? And where we're going with all this is the exact area, so I'll say area equals, so no longer area is approximated by, but area is exactly equal to this expression right here as n approaches infinity. As the number of rectangles, because n is the number of rectangles, as that number of rectangles approach infinity. So as that would happen, those widths would get smaller, but you know, it would end up being like little rectangle here, little rectangle here, little rectangle here, little rectangle here. You know, more rectangles, less overestimate, less underestimates, and actually closer to the exact value. So what we would do is we would say the limit as the number of rectangles approaches infinity of the summation from I equals 1 to n of f of a plus I delta x times delta x. Trying to think what the best place to put this. Okay. That's a great statement right there. This is super powerful. And we're going to do a problem to solve for the exact area. We're going to apply them. We're going to do all that. However, before we do that, I do need to remind you of some rules and some formulas that deal with summations, okay? So, summation formulas. Rather than in the middle of it, me saying, hey, remember this, and hey, remember this, and hey, I'm just going to tell you right now, and then we'll apply it here in a minute. So, summation formulas and properties, I would say. So, if you have the summation, and I'm guess all this is from 1 to n, whatever, I equals 1 to n, of two things, ai plus bi, then you can split that up. You could write that as the summation from I equals 1 to n of ai plus the summation I equals 1 to n of bi. We've seen this property with limits, we've seen it with derivatives, we've seen it with everything else. So it's a summation property. There's also a constant multiple property, where if you have a constant times a function, then you can pull that constant out, so you can say c times the summation from I equals 1 to n of a sub I. Those would be the properties. Here's now the actual formulas. The summation from I equals 1 to n of 1. So that would mean, like, you don't need to write this down again. When I equals 1, you've got 1, plus when I equals 2, you've got 1, plus when I equals 3, you've got 1, plus when I equals 4. You know, so you're adding 1 every time. And how many times are you adding 1? Well, you're doing it n times, so that's just n. Think about that. It's not pre-cal, so I'm not going to go too much in detail, but if you're curious about this, I can explain it. If you have the summation from I equals 1 to n of I, that's a fun formula. That's 1 plus 2 plus 3 plus 4 plus all the way up to however far you want to go. That's n times n plus 1 all over 2.
Oh, that's Carl Gauss formula, right?
The Gauss formula?
Yeah, the Gauss.
Yeah, the Gauss one, yeah. That's where he's like,
Yeah, that one.
the teacher told him and said, hey, you got to figure this out, you know, and it kind of, it was like a, the way the story goes, it was sort of like a warm-up exercise for the class, and he's like, all right, everybody go add up the numbers from 1 to 100, you know, and everyone's all scribbling down, and the one kid comes up and he's like, here it is, and
Yeah.
they figure that out. Anyway, so yeah, but you add the end in the first one, so anyway. Came up with this formula, it's pretty cool. N times n plus 1 over 2. I am going to, if you multiply that out, you get n squared plus n over 2. I think there's a reason why we might want to go with this one later on. And then summation from I equals 1 to n of I squared. That would be like if you had 1 plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16, plus so on and so forth. And that formula is already over here, yes. N times n plus 1 times 2n plus 1 all over 6. I've never seen the derivation of that formula. That might be kind of an interesting one. It's all algebraic. If you FOIL all that out, I'll just tell you this because we'll want to substitute it later, and I'm just going to say, hey, it's this, whatever. It's 2n cubed plus 3n squared plus n all over 6. So we'll be utilizing some of those. Formulas here in a second. So go ahead and get out your 5B homework. That was the area under the curve. We are going to do just one problem. We're going to do number 1. We're going to do it the limit way. So here's our function, negative x squared plus 12. And you'll probably, I wanted you to have that out just so you can see the graph on your paper. You don't need to write it or whatever, but we're going to, I don't know if you wanna write this on that homework, or if you wanna write, I'd probably write the process that we're gonna do, on your notes, but just have that out in the table for you. And we're gonna find the area under this curve between -2 and +3. So we're going to calculate all of this area, everything, the exact all of it. So no approximations. We're going all the way here. All right. So the first thing we're going to do is we'll write our formula down. So the area is equal to the limit as the number of rectangles approaches infinity of the summation from I equals 1 to n of f of a plus I delta x times delta x. This process is probably going to take us about 20 minutes, just maybe less. But don't worry, you only have 20 homework problems. Get into it. All right, where delta x equals b minus a all over n. In this particular problem, we've got a is our starting point, so -2. B is our ending point, so +3. So delta x is going to be 3 minus -2 over n, so 5 over n. Alright, so we'll go ahead and start plugging this in. So area is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of a, so -2, plus I delta x. I'm going to write that as I times 5 over n times delta x, so 5 over n. That's our starting point. Everything now is algebra. We're going to take this and simplify it all the way down to actually getting a number, and that number is going to be the exact value of that area. All right. So here we go. So gotta write that limit out front. Gotta write that summation out front. Then we have to say, all right, this is f evaluated at -2 plus 5i over n. And what that means is I've got to take this value right here and substitute it in for that x squared. So I'm going to put a bracket here just to kind of start everything off. So it's going to be negative parentheses -2 plus 5i over n squared plus 12 times 5 over n. So this was f of blah, so I'm taking that whole blah and substituting it into my function. Function was -x squared plus 12, so it's -x squared plus 12. Stephanie, any questions on that part? Okay. Well, now we get to FOIL this thing out. Alright, so we'll do that here in a second. So, next line, we're going to just have good habits here. Write the limit as n approaches infinity. Write the summation from I equals 1 to n. Write an open bracket. I'll put a negative in a parentheses. So if you remember, your if you have a plus b quantity squared, then that's a squared plus 2ab plus b squared. So it's the first thing squared plus 2 times the first thing times the second thing plus the second thing squared. So inside my parentheses, the first thing squared is, so that it's -2, -2 times -2 is +4, plus 2 times the first thing, so -2, times the second thing is 5i over n, plus the second thing squared. So the second thing is 5i over n. So 25i squared over n squared. Put the plus 12. Close bracket times 5 over n. Jeremy, let me know if something doesn't make sense here. Catch me if I'm sick. So it's just algebra at this point. So all right, good habits here. Limit as n approaches infinity. Summation I equals 1 to n. Let's go ahead and simplify inside the parentheses here. So the 4, that'll stay the same. We'll just multiply here. 2 times -2 times a 5. So that's -4 and a 5. So -20i over n. We'll keep this the same. 25i squared over n squared plus 12. Keep the 5 over n. So the limit as n approaches infinity. Summation I equals 1 to n. Are y'all comfortable doing maybe a couple things at the same time? Just 2. First thing I want to do is let's imagine that we've got that negative distributed across there. Okay, so when I do that, I've got a negative, positive, a negative. When I add that 12, so I would have a -4 plus a 12. So 8. And then this is plus 20i over n and minus 25i squared over n squared. All right. Then for our next step, we'll distribute this 5 over n to each one of those terms. So we've got limit n approaches infinity, I equals 1 to n. 5 over n times 8 is going to be 40 over n. 5 over n times the 20i, that's going to be plus 100i over n squared, because the denominator is n times n, minus 5 times 25 is 125. I squared n times n is going to be n cubed. All right, now this is the point why at the beginning of the lesson I said the motivation is this is going to take us to give us all kinds of really neat applications. Remember I said it gets kind of tedious? Yeah. It'd be nice if there's a shortcut for all of this. There is. But you cannot appreciate the shortcut until you at least go through at least one problem going through this to see that it's legitimate. Trust me, it adds some validation in your mind here. So, all right. We are now going to apply the summation property, where you have the summation of 3 things, a plus b plus c is equal to the summation of a plus the summation of b plus the summation of c. Okay? So, I would say I'm just distributing that to the summation, but that's not really the technically proper term here. So the limit is n approaches infinity. I'll put a big bracket right here, and I'll write this as the summation from I equals 1 to n of 40 over n plus the summation from I equals 1 to n of 100i over n squared minus the summation from I equals 1 to n of 125i squared over n cubed. And that's why a few minutes ago, I said, hey, remember your summation formulas. The summation of two things added together is equal to the summation, or this is equal to the sum of those summations. Okay? Alright, next thing. We need to figure out, and if we had more time, if we had like an extra week and a half of school, I would have us where we spent a day working on simplifying these type of expressions. But in reality, we only need to know this for this one step that I'm about to show you for right now. So we're not gonna spend a whole day on it. That was your pre-calculus teacher's job. All right. I hope I did good last year. And the idea is we're asking ourselves in this summation statement right here, what is actually changing each time? And the answer is the 40 is the same every time because it's not part of the counter. The n is not changing because it's always the same. So effectively, this 40 over n is a constant. If we were to think about what's going on here, this is 40 over n plus 40 over n plus 40 over n plus 40 over n times. So this right here functionally is a constant. It's basically this thing right here. It's a c. So we can pull that out. So we can write this as 40 over n times the summation from I equals 1 to n of 1. Plus, and I'm not getting lazy here, just getting excited about the summation simplifications here. So make sure you have your limit statement up front. On this summation term right here, what never changes for each one of those terms? The constant, which is the 100, yes. The I, no. The I is going to change each time because it's going to be that's our counter. So 1 plus 2 plus 3 plus 4. So the I has to stay inside here, but the 100 is going to be part of each term. It's going to be 100 I over n squared plus. So like 100 times 1 over n squared plus 102 over n squared plus 100 times 3 over n squared plus 100. So the 100 over n squared is same every time, and that's what we can pull that out. If you're not sure on that, you take my word for it. We can talk about it later, but we're just going to move on at this point. The I is the term that's changing. Over here, same thing. The 125 and the n cubed, that is constant. You can factor that out. So we can pull out the 125 over n cubed, and we've got the summation from I equals 1 to n of I squared. And that's really nice because that term right there, summation from I equals 1 to n, we've got a formula for it. This part right here, summation from I equals 1 to n of I, we've got a formula for it. That's this one. And this one right here, summation I equals 1 to n of I squared, we've got a formula for that. So we're going to convert these summation things into an algebraic expression, which is good for us. So here we go. Equals the limit as n approaches infinity. I've got the 40 over n times, class, what was this first summation formula? From I equals 1 to n of 1. Yep, is n. Plus the 100 over n squared. Somebody else? What was this formula right here?
En times n plus 1 over 2.
Yep. We'll write. Yep. I'm going to write it as the distributed form. So the n squared plus n over 2 minus 125 over n cubed. And I'm going to write that as the distributed, the full term there, 2n cubed plus 3n squared plus n over 6. Believe it or not, we're like 2 steps away from being done at this point. To make things easier for you to see, we'll go ahead and combine this. So the limit as it approaches infinity of the 40 over n times n, those cancel out, so that's just 40 plus the 100, the 2 is going to reduce to a 50 in your numerator, and we'll just go ahead and distribute that times these two there. So 50n squared plus 50n all over n squared minus so I've got 125 times this term, 125 times this term, 125 times this term, okay? I'm really just going to focus on that first term, 125 times 2n cubed, so that's going to be 250 n cubed plus blah, 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 blah. I'm not really going to care about this because in a second you'll see why. But those other terms are not the dominant term in this expression here. Y'all, if y'all remember when we were talking about limits, when you end up doing a limit of something over something else, a polynomial over a polynomial, and you've got a cube, a squared, and a single term, which one of those is going to be dominant? The cube. So I'm going to say blah, 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 who cares, all over 6n cubed. Alright? And this is where chapter 1, those weeks we spent on limits were really helpful. Because remember our limit property, the limit of a summation is equal to the summation of the limits. So you could apply, say the limit as n approaches infinity here, plus the limit as n approaches infinity here, minus the limit as n approaches infinity of this term right here. So rather than, I'm not going to write the limit on each one of those, we'll just discuss it out loud. What is the limit as n approaches infinity of 40, class?
Isn't it?
Big guess, it's fine.
40?
Yeah, it's 40. Because there's no n, right?
Yeah.
It doesn't change. It's just 40. Plus, now here, the limit is n approaching infinity of this over this. If you remember, we got to figure out who's the winner, who's going to win, numerator, denominator, or tie.
It looks like tie.
It's a tie because the coefficients, or because the exponents are the same. The tie goes to the
Constant, right?
yes, the constant. It's the ratio of the coefficients. So we've got a 50 and a 1 there, so that's a 50. I could say 50 over 1, but minus. Once again here, who's going to win? Numerator, denominator, or tie? Tie. So tie goes to the ratio of the coefficients, so 250 over 6. You got a calculator, right? What do you got? 48.3 repeated. What we're trying to find again now?
The area under the
Area under the curve above the x-axis between A and B. What did we get when we used the rectangle approximation?
50.
We got 50. So we got our area was approximately 50. We found out the area is exactly 48.3. Looking at our 50 number, according to all this stuff, 50 was an overestimate. Does that look realistic that 50 would be an overestimate? Because we've got some, those rectangles are kind of pushing it a little bit. There's some here that are underneath it, but it'd be nice if the answer was 50 exactly, and it was a nice and round number, but it's not. It's actually 48 repeated. That is, but the 48.3 repeated, that is the exact area underneath that curve. It's not an approximation. it's the answer that you would get if you were to add up, if you were to split this into an infinite number of rectangles that were infinitely small and saw what the trend was going towards. And the trend is going towards the stopping point at 48.3 repeated. Okay. Now, calculus would not really be used a lot if you had to do this process every single time. Okay? Even if you had a computer to be able to do it, it would be kind of annoying. But fortunately, somebody at some point did this enough times that they started to notice a trend. Okay? They also decided to make a notation for it. All right? And so the notation that they used was this. They said, rather than writing the limit of the summation, blah, 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 they said, well, the function is, we'll just write f of x. We've got x go along here sort of as a dx. And then they did this thing. So let's write this elongated s here, and we'll put our lower bound here, -2, and we'll put our upper bound 3. And this is the notation that they used to talk about the area under the curve, but above the x-axis, between -2 and +3. Now Stephanie's looking at that, and what are you thinking? What are y'all thinking? It's the antiderivative. That's the antiderivative formula. That's the easy one, right? That you wanted to grade because it was super, yes. Okay? And so it's like, it wouldn't be really nice if there was a way of connecting that process, which we're really familiar with, the antiderivative process, to give us something really meaningful. And the answer is yes, it is. Okay? Now, the thing that I haven't showed you is how do you connect that antiderivative process to deal with this -2 and the +3. Alright? And it's a super awesome formula for that. It's called the fundamental theorem of calculus, and you're going to have to wait till Monday though for us to connect those dots. Okay? That's going to connect the area under the curve to the antiderivative. Okay? After much prayer and suffering, I have decided not to give you an assignment based on this, but just let you appreciate the work. And we'll look for the shortcut on Monday. Sound good? If you haven't finished antiderivative promotion, take care of that. We'll grade that on Monday. All right. And when do you feel that?